till about 12:30 or so for about an hour, and then maybe open up some time for a few questions or anything like that. And so I think last we were working on calculating the diffusion term. So we had worked on the pressure gradient, and now we are working on calculating diffusion. Okay, and so we were talking about the fact that we have this K value, which is that stiffness. How is the pressure going to change? And we were talking about realistic values, and the fact that that K number is a small number or a large number. A large number. So we would expect that. Oh, right. Sorry. Forgot to do that. Is that good? Maybe a little bit bigger. Okay. So we were talking about, this K value here. It's going to be a large value. So what does it tell us about the density values for a particle? So talking about particle I, what is that density value going to be? Right, close to rho naught, or reference density. Yeah, that's one of the things. You have P's. I have to add a little serif to the P, right? So it's like smooth P and then a little serif P. Start doing that, adding it to everything.
I think it helps if there's the real.
Well, no, the P is pressure.
No, I know.
Oh, right. Yeah, so then we have, how could we could calculate, because the particles represent ideally they should represent what's happening in the fluid around that particular spot. So we want the difference between rho naught and rho I to be approximately the same. So we have a problem in the code right now. Let's take a look at what's happening. I need to back out of this. So we go over here. So I'm going to go and increase the number of particles. Reset. So we added gravity, but yeah, we're gonna try and fix or see what's happening, but the fluid isn't acting like what we are hoping for, right? That's the net effect there. Okay, because when we left it last time, we had let me get our example 18 going. Can I close others? Yeah. Get rid of that. Turn that off. Ignore that. Okay, so we have a few things going on. So we can, for one, I decided to change the density function. So if I take the exponent of density, we can pass in values anywhere from 0 to 10, okay? 0 to 10, and throw that into our calculator. If we were to take 10 exponent, oops, I think I got to increase to get the, there it is, EDX, then we get 22,000, okay? And take e to the 0, what do we get? We get 1. And the reason I did that was looking over here, density, right? Air is 1, approximately, right? As far as numbers go. Water is 1,000, but we were looking at Wikipedia, and you get peanut butter is like 2. So in order to get 1,000, I want to say if you plug in 7, you get about 1,000. Okay, if you plug in 8, you get about 3,000. So if you keep your numbers between 7 and 8, you're getting the water values, and then up from there you get into like metals and things like that are really dense. So I figure that using the exponent to kind of map the density is a realistic way of getting those density numbers into our calculations. And then as far as the bulk modulus goes, this is a case that 1.5 gigapascals. We're going from, and then glass is 40. So I figure anything that's like values of 10 or so, like if you get values of 2 and less, this is going to affect the speed of sound. So I thought, I could change this so that we are talking about the speed of sound squared, so it's a linear factor. But I still would like to play with it to figure out what is the appropriate range. But for right now, it should be like 1E9 times the whatever the KS value is, because we are throwing in numbers from 3 to 0. And I should actually make that let's do this, because if I throw in a value of 0, just put air. This is the smallest number you could have. Math.max. Okay. That looks correct. So if we throw in this is 0 essentially, then objects. I should probably change the default so we get like 100. So if I throw these numbers, like realistic numbers, you see what happens to the simulation is it like explodes. I have a feeling that if I were to like say 1e minus 10 times that, basically like bring it all the way down again, you'll notice that the simulation slows down immensely. So it's kind of weird that the KS, and I think the collisions are not, oh, did I turn them off? Let me hit reset. Let me go with less objects. This is something that's also, for some reason, if they go all the way down, they're not, the collision isn't exactly acting appropriately. Okay, so we got to fix that. So the collision is actually causing not a numbers to appear, probably because we're getting some extreme values. Boom.
Still not working?
Huh? Oh, no. We're examining all the ways that it could go wrong. So if we plug in wrong values for our KS and our density, then it acts like a speed control. Like KS acts like a speed control, which, right, because we I like how the more you work with this stuff, you start remembering facts that are only going to impress your friends. Right? So I never would have memorized the speed of sound, but now I do. I understand this way more. So, as KS goes up, then, then your C squared value is going to actually that's C. The speed of sound equals the what will end up happening is the square root goes away. So KS is going to act like a giant speed control because it's, we're measuring that, in the billions, right? So 1E9. So we're talking gigapascals here. And we can go all the way from like basically 142,000 pascals, all the way up to where the range we have now is 3 gigapascals, so like a little more than water, divided by our density, which our density is, we're talking numbers from anywhere from like 1 through 22,000. That's the range that we're giving it. So you missed this. I had changed the density. So density goes from 0 through 10. And if you apply the e to the x, that gets you numbers from 1 through about 22,000. So if you put a number like 7 or 8, that's about where water is. So 7, e to the 7 is 1,089. So you're approximately at water if you pick 7. And e to the 8 is 3,000. So we looked at peanut butter. So actually, that's almost exactly the same thing as peanut butter is 7. Perfect. Okay. So anyway, because Ks is normally about a million times bigger, it's like 2 orders of magnitude larger than the density, it's going to act like a speed control because our pressure, we're measuring our pressure gradient. So if we're saying that our pressure gradient is small, then basically what happens is that or I guess what's going to happen is that you get little acceleration, right? So the gradient of pressure is basically what we're using to determine acceleration. So Ks naturally is going to affect our acceleration. So just by looking at the equations, and we can kind of do that here.
Does a correctly speed limit create shock waves at the speed of sound in the material?
I hope not. I say I hope not because those kinds of things really make it difficult to I mean, hopefully it doesn't create a shock wave. I don't know. I don't know if we could see a shock wave as coarsely as we're simulating the water. Okay, I'll put it that way.
Well, I'm just wondering, like, if the system will the system produce values over the speed of sound? Based on the numbers.
Oh, the velocities?
Yeah.
I think it's possible the way it's acting up right now.
Fair enough.
Yeah, I think it's possible the way it's acting up right now. Okay, so this is how we were calculating the pressure gradient, although I'm looking over here that maybe there might be a slightly better way of adjusting that so that we have a, yeah. Actually, no, they're just saying that if you look in different places in the computer graphics literature, you get a different formulation for the pressure gradient, but the one that we have is better. And the reason why is because the one they have mentioned here would cause a asymmetric relationship, or I mean a symmetric relationship, but we want, because ours is kind of derived directly, so we don't get that problem. So you have to be careful how you do it. So you want to do it the correct way. I'm assuming we're doing it the correct way. So this is how we should do it: pi over rho I squared plus pj over rho j squared. Okay, so at this point we need to add some kind of debugging, right? So I'm gonna change this back so we're getting realistic values here, and then what we want to do is c squared equals ks over density. Okay, so when we're updating everything, we have Pmin and Pmax, and then Umin and Umax. So I set max to a large negative number, and actually I should probably set this to even, wasn't thinking about this, but set those to even, well, it shouldn't be a problem, but we want to keep track of our maximum velocity, minimum velocity, maximum pressure, minimum pressure, and when we do that, I do those calculations when we're applying forces and when we're calculating pressure. So I just do the min and max values, and then I color them. So the way that we color, I add two check boxes, so we can either visualize the pressure or we can visualize the velocity. Okay, so red is mapped to pressure, green is mapped to velocity. So if we are hitting maximum velocity, then we will see green and blue, and that is which color? Cyan. Yeah, so cyan. And if we're visualizing P, so I guess that technically they could go to white. I guess maybe we should change the background color instead of it being white. Yeah, we could do brown.
It's color.
I'm sure I can say much else in Browns defense or support.
Okay. Yeah, so if we're not visualizing everything, everything's like blue. And pressure. Let's change our default objects so that every time we reset we make an update on our program, we're not getting, we could go with 50 for now, just because we're streaming and that's causing issues. Okay, density, let's change density to that of water, peanut butter. And the KS for peanut butter, we'll just stick with water. It's oily peanut butter. I don't know. I don't even know what that means, but okay. Okay, so we go here. Now there was some suggestions.
Do you mind if I dim the lights?
Yeah, go for it. That
Is this okay?
I think it's
This is
okay.
why.
Okay.
This is how I live my life.
In the dark. Okay. All right. So for the sake of just being able to see anything that's happening, we're gonna going to remove. Whoa. Okay, so this should slow down. I think ironically, maybe we should get rid of gravity too. Because at least when we weren't applying gravity, then...
What does cyan mean again?
So cyan means maximum velocity. So if we turn off pressure, now that's acting weird, I think.
Yeah.
So they're not conserving energy. I can guarantee that. Getting more strange emergent behavior.
Yeah, why are they dripping? It wasn't doing this before, was it? When we left it off.
No. Okay, let me see if we put the pressure gradient. So this is now, how do we debug, right? So I think what would be helpful is if we could visualize what is the, we could at least start with what's the minimum and maximum velocity we're seeing and minimum maximum pressure. Okay, so let's go ahead and do that.
And then check if that's normal.
Right. Okay, so I don't remember if we have these range rows, but I don't remember if we have something similar for, let's check. Instead of creating a checkbox, we're going to create a text box, not like a label. We're going to call it a div row. Okay, so class equal div column right, ID equals so if we do this, then we should be able to set the contents. So we'll add another function here, set okay. This will be pretty easy. E dot inner HTML equal content. String. Okay, so we have some good documentation there. We will let's add it to the top. Controls, we'll call this U and P. Those look like terrible names for variables.
They won't come back to haunt us later.
Probably.
Except for the tell us up to sleep tonight.
Okay, so then inside of our update functions, we can call set div row contents U to be umin Is there like a way to format? We can to fixed. 5. Sure. Plus max. All right, let's see what happens here. Let's just check for errors. String of undefined. Human undefined. I think what it is that they have human. Maybe we should do it in here. Sync controls. Oh, that's why I think so. Okay, so we're get range value. F support radius. Oh, P. Oh. Well, maybe we're something I hadn't thought about, but maybe when we're creating it, left content, right content. Let's let this do this again. And sync controls. Oh, we're asking for P. Okay, that was us just not. We must have been asking for P in a different life, and we just okay. So okay, now we're caught error. Play, refresh. Okay, just okay. So velocities are going nuts. So yeah, so they are. So I guess technically the velocity should never move faster than 1 meter per second, right?
Whatever the speed of sound is.
C, so yeah, so the square root of c, that should be the maximum that it can move. I think that's a safe, and then eventually we get to not numbers, which is when it decides to kill over. So when we get to u gradient, oh wait, what was that? Accumulate. Okay, so there's our forces SV dot accum. So there's our magnitude. Okay, so if SV dot U mag is greater than this dot C, so we need to get, let C equals math dot square root this dot C2. Okay, so if the magnitude is greater than that, then SV dot U dot scale. We want to go what's that?
So
Oh yeah, that local variable. Okay, so if greater than the speed of sound, c divided by the magnitude. This will normalize it to a length of 1. This will multiply it by the sound. That look okay? All right. And that is the speed of sound. Well, that's -2, so those values look okay. Still glitches out. Wonder why that's happening. I wonder if it's because we're allowing it to we're allowing the force to be. So let's think about this. If it's meters per second squared, then our force should be not, I guess, should not be allowed to increase more than what c divided by the time step, right? Does that make sense? It's got to be related to time steps. The force. So when we're allowing the total force should be, I guess, proportional to the maximum amount of speed. Like are we ever allowed to accelerate faster than the speed of sound? I guess that's the question there.
Energy is supposed to get dumped into the weight behind you.
Yeah, well, because we're updating we're updating position and we're updating velocity. So I wonder if we have to make sure we're not allowing you to kind of go past that at this point. You know what I mean? You see where I'm... I guess what we could do is copy and paste this. So after we've accumulated u, then we scale it. And after we accumulate it, then we scale it. Let's see what happens if we do that way.
Better. Ish.
And then it goes out of control again.
don't know, I feel like the pressure element is just
well, it could be the pressure gradient is
because they're being shot to all the corners, which means that the internal repulsive force is the fluid
Right.
system is. So I just like that should be pressure unless we're doing something with diffusion.
well, if we add the collisions, then technically nothing is allowed to be like a superstate. In other words, you don't have particles like on top of each other. Because if the particles are on top of each other, then that's going to cause the pressure gradient to go up, because then it, and that's why they're acting normally over here. But if we
That's with collisions, right?
that's with collisions.
It looks like I know something about her pressure. That would be my assumption. Like the driving force here is pressure, right? Like that's what causing anything to do anything.
Right.
Pressure's too much.
I have another idea. Well, I guess the velocity is the big issue there. Okay, so let's add p. Let's see what p's doing. So I guess before we get too crazy, let's just let that be what it is. And let's add p. So let's go to scene controls, because I think the pressure has a lot to do with it. And we can see what happens if we, I guess, turn it on. So if we add P, we do Pmin.
Well, also one other thing.
Oh, you're right.
A problem is the walls aren't providing any pressure. In the standard model.
They would. Okay, so now this, I mean, to me, this looks like a big issue. Because the rho, I guess the force due to pressure it's like a factor of what, 100?
Yeah.
Now let me see if we, so sync controls over here. So if we, and this is not even scaled, so if we do this, 1E9 times, then the pressure, you see how the pressure just like, we're talking like really huge numbers. This is why I guess that's a big issue. Whereas if we did like, if we divided the speed of sound basically by a third, then the pressure would be changing by a very, very little. If we turn the collisions on here. Okay. Okay, so let's continue doing this. The other element, let's see what happens if we disable one or the other. So the SPH. So if we turn off the pressure gradient, let's see what happens with diffusion. sv.pgrade.add. Oh, we must not be setting the pressure gradient. Let's go to initialize. This.p gradient.reset. This.u gradient.reset. Okay. So I think the problem here is that okay, so yeah, because we don't actually construct the objects yet. So let's construct those. Okay, so if we have no pressure gradient, then although I'm thinking that technically for the diffusion part, we calculate that.
Are they moving?
I can't tell.
Kind of looks like they're dancing a little bit. I might be
Oh, yeah. Let's turn on collisions. Put a lot of them. They might be moving. Let's look at the diffusion code. So DDW, velocity, this dot new times DDW, m dot density. Okay, and when we calculate the density pressures, that should be fine. Maybe we can use our, are we using our real values here? Yeah. Let's turn off the pressure. So there's no velocity at all. Actually, we can see that here. There's no velocity. We can see that pressure is really high. That tells me that whatever we're calculating to be the reference density is really low. Somehow that number is really low. And I bet it's because when we calculate density, like the initial density, we're getting, right, y, so 10 minus y times 9.8 times the density. So this is a really small number. So we must be calculating the individual masses to be way too big. That's what I'm thinking. How about we do, let's do this. Let, mass should maybe be constant, right? So we have the number of particles. So
actually, we're inputting a density of the substance, right? So if we know the size of the particles, we should be able to calculate the total mass pretty readily.
this dot density, I'm trying to think here. I know we're like a 4x4 block. Let's just make a guess that the volume is 16.
That we don't have a radius number.
I think we're simulating massive particles inside of this thing when it should not be so. Does that make sense? In other words, our density is, maybe we could throw this in. Let's look at let's calculate O1 density minus rho naught. Let's find out what our averages are. We want to get that down to a very small number. So minimally speaking, we got a really big number there.
Well, a really negative number.
Yeah. In other words, the mass is really so is W? Is W acting weird?
Well, what's rho naught in this case?
The rho naught is the reference density. So maybe, yeah, well, let's see here. Let's see what rho naught is coming out to. Yeah. Okay.
That looks like it was the bulk of it. So I think density is coming out fairly small.
Justification for rho not being what it is. Density times gravity.
Yeah, rho times mass times height. So if you have density times g times height,
Well, did you see what density is by itself, or did we just show it with rho naught?
we showed it with
So that's rho naught.
yeah, this
Which is really,
what's weird about this part is that oh that's okay. Maximum of, okay, we're just calculating that wrong. I don't remember what I had before. We should be okay. That makes, we just were, I overwrote this, I think. Okay, so
rho naught is like 10,000.
yeah.
Is that
Okay, so let's check the density of the particles. This making more sense. Okay, so anywhere from like 200 to 1400. Okay, and then so then if we do minus rho 0,
Shouldn't the number we put in be the upper bound, not the lower bound of the density?
well, the particles could have different density because if they're close to a bunch of other ones, then the density, we're calculating the local density around a particle,
Oh, okay, yeah.
which
I
could be
was
variable.
The density wrong.
Right?
Because that was about water, roughly, right?
And we want this to be able to possibly be negative or to be positive.
it's negative 10,000? Small.
We want it to be basically approximately equal to rho. Okay, so I think that initially we created a we created the particles too thick. Now, if I put the mass all the way down, something low, now we can't see the particles, but I would expect this number to change. Okay, so it goes from minus 10,000. If we go really small, it didn't make much of a difference. Let's check the density of, so if we go really low, okay, if we go really high, then that has a decent amount of swing to it. Maybe what I need to do for density is calculate the total density for the particles that we have. Let's try that. We want their mass. Divided equals so if we do this, then we guarantee that that the mass won't. I guess we're calculating the mass as
That actually calculate anything other than what dot n is going to tell us.
okay. Now we're not simulating the pressure gradient yet. I guess because the velocities aren't. Let's add some initial velocity. Let's see what happens. If
Okay.
I guess we have to change the speed of sound too. Because the speed of sound will affect. Let's give them all. Some initial movement. Oh, okay. We're not actually changing their initial particle velocity. Guess I need to do that. Well, kind of. It's the pressures are changing, so I guess that's a good thing. We're not simulating the pressure gradient, but we could. Let me delete that because that's not what we want. I guess when we're doing reset and I'm doing the initial P, let's just copy the okay, now this is changing. Oh, That's its own set of problems. I have wondered if we should like calculate the total momentum of the entire system and then make sure that the total momentum is conserved somehow as like a check.
Okay. And it eventually goes to the walls because the walls aren't bending back enough.
Okay, so I'm gonna we're just gonna create some random fluid velocity. And then the walls are gonna cause issues. I bet the walls cause issues because it wants to push some out of the wall. And then because it can't go outside the wall, then it keeps compounding the velocity, ever trying to get it out of the wall, but then not able to do that. So I'm thinking when we bound the particles that maybe because we're not doing anything with the fluid velocities. So I guess if it's outside, there's the velocity right there. Let's do this. If we're outside, then we set the fluid velocity to 0 in those directions. What do you think? In other words, technically if it's not moving left, it should never move left. And if it's not moving right, then it should move right. So let's clamp, in other words, let's clamp the let's clamp the fluid so that they're not they don't have that. I'm thinking that's what's happening, that the velocity, if it's on the left wall, then the velocity keeps increasing because you're taking the difference, that function for the Laplacian is uj minus ui. So if your velocity then is getting greater and greater than 0, but you're being clamped, like you can't go outside the box, the velocity is still increasing, and therefore you're creating an increased force. So let's see if that happens here. This is moving really slow, but then we can maybe add the pressure back and see. I almost feel like it's getting even slower. All the particles affect each other. Oh, okay, interesting. I'm changing the support radius, but if I increase the... Okay, they're all technically 0. Oh, because they're not moving. There's no pressure. There's no pressure, there's no velocity. So if I hit reset, cool. Okay, well that fixed some of the problem. Okay, so part of it is they're losing control. So this is where the analysis comes in. You're like, why are the particles going crazy on the edges, but they're not going crazy in the middle? So this whole system should be slowing down because of the diffusion, right? So I wonder if we turn Ks up, then that's the stiffness, right? If we turn it down, yeah, look, okay.
The thing is, they're just coming to a stop on the edge. Like the thing is, the repulsive force wants to push things out, and they're just hitting it in like Okay, cool.
Right.
So is it reflection? So negative, the aspect of you that's going in the wall's direction.
All the velocities are decreasing.
Although, for
Okay.
it's not terrible for a steady state fluid. I just think there's a little one sugar on the walls.
Right. Okay, so now let's. I think the diffusion is a little bit more under control. So now let's see the pressure. See if the pressure is still okay. The pressure is still going crazy, I think. Let's see here. Reset. The force due to pressure is still really high. It's doing something.
Well, it's immediately going to the wall and getting a zero after velocity.
Well, we're not letting the velocity do anything right now. Let's turn on the collisions. Not in numbers. Collisions sometimes cause issues. Oh, because we're adjusting the velocity v. Okay, so over here we were measuring okay. May have something to do with the fact that we're allowing the particles to be like shared. That's 0. Well, the pressure gradient should then be like no pressure then, if that's the case. Basically saying 0 times that. So when they get to the corners then, they're not ever going to go anywhere. Interesting. I think that's something to fix. Okay, we were calculating. Okay, so density minus rho 0. That p vent, the p min. This is still really high numbers, and let's just quickly see if rho naught is changing. I don't think rho naught should be changing, but our rho naught value is basically what, 250? Because it's dependent on our mass. Right. Okay. But then the densities is much bigger. Anybody guess why that? Okay, I think I know what's going on here. If you set the support radius super tiny,
all the way out at 3 so normal numbers.
let's see here, 250 is the So I think what's happening is we don't have a conservation of mass. I think if you added all the densities up, then right, because we're adding the particles density, right? So that automatically gets a 1. then if we add up neighboring densities, then that's going to increase the density. So we're always kind of positive. So that means that this number is always going to be more or less larger than the reference density. Because, I mean, think about it. Rho 0 is going to be 25 because there's no change at all in each particle's value. So as we add neighboring values together, then it's always going to be positive. So we're always expecting some kind of positive pressure. Yeah. Maybe it's okay for the density to be 0. Probably not. That shouldn't change anything anymore. Well, this pressure is going to be used to define the force. So if this value is 0, then there's no force. And the only way that this is not 0 is if the particle density is different than the reference density. So if we say that, imagine a tank of water, and let's just say that like one corner of it was thicker, if it had more density, then that is creating pressure. And then that's going to cause those, because water is going to take the shape of the container. So it wants to spread until you have even density throughout the whole thing. It's consistent. So what we're seeing here is there's, I guess there's no, I think what we have to fix here before next Tuesday is to get the reference density correct for the volume, and then in turn get the particle densities correct. So I know we have the radius here. Okay. Right now that equals the mass, but I want to set that equal to a minimum value. Oh. Let's see if that changes. We set KS very small.
So we're seeing white. What's that?
White means, yeah. Well, the fact that they're pink means that they got lots of pressure. Now notice how when we turn the mass down, the pressure is going down. Let's see if we add some variation. Ooh, variation looks good. I wonder if we're actually like simulating like the real like atomic speed.
Yeah, if we were going down to that level, we could skip all those fancy like pressure things. It should be like, look, particles, mean path length, done.
Yeah.
I mean,
Yeah.
I feel like the system is too high energy, like the effective temperature
Yeah.
of the system is too high.
I would agree with you there. Okay, so we need smaller radiuses, smaller initial radiuses. Okay. Okay, so we need to more variation, small, more particles. Collisions might help. Nope. KS needs to be small. Oh, drag. Let's try drag. I guess the other thing too is we have the fluid volume, and then we have drag's only affecting the actual velocity. Okay. We're going to work on this some more next Tuesday. But I think what we've learned is that the pressure is one of the biggest issues we have to fix. And that is partially caused by the fact that our density, our reference densities and our actual particle densities are vastly different from each other, when we would expect them to be very, very close to each other. So that's where we got to figure out why is that the case. Okay, I have a feeling the way to fix it is just to get the particle mass correct, so that it. In fact, if we're assuming that the radius of the particle, right, corresponds to the mass, we probably figure out what each like blob ought to be. Like each, if it's a bigger particle, then that equals that certain volume of density, or I guess mass, and be able to figure that out. So we'll continue working on this next Tuesday, and hopefully get some stable fluids going. So I would encourage you guys to play with it. Go ahead and sync up to the repository, and then see if you can play with why the densities are incorrect.
So how hard, or do we delay that? Fix it by Tuesday. That's the
Yeah, that's our quest, is to we'll just have the homework due next Thursday. Is that?
I feel like we should go back to the broken one.
Well, this one I
don't know. I feel like at some point we just went way off and lost it. What component it was?
Oh, it's the KS, the speed of sound. Because if I remove this, if I remove that, then the pressures are fine.
So it was when we tried to go to more realistic values.
That's correct.
Okay, gotcha.
And that's causing the pressure to change.
darn it, realism.
Yeah.
Darn it, realism indeed. So,
Well, it's a simulation.
It's kind of the point, though, is to be as accurate and as interesting.
Yeah. I guess to close this out, let's add the diffusion real quick and see what happens if we use unrealistic values for the pressure. Then let's see the diffusion working in conjunction with that. Oh. Okay. Yeah, so if we set the viscosity low, I guess we could give it some initial motion, but if we set the viscosity low, it almost slows down. Oh, so
Really interesting. There's like a threshold at which they allow themselves to separate.
Right.
Tiny little fluxes.
yeah.
I don't
Okay.
know, should there be like an adhesion factor as well that like matters?
Well, that's what the stiffness is all. That's what the KS is, I think, supposed to do. The pressure, because if you remember viscosity, earlier when we were talking about fluids, viscosity is one of those things that you could assume that it's not viscous, and that simplifies the equation. So in other words, you get rid of the diffusion. Just kind of says how did the velocities kind of spread throughout the whole thing. So you could.
I'm used to thinking of the viscosity as the internal friction, as opposed to like the particles not wanting to leave each other.
I think the pressure has to do with that. So you have outside pressure from the walls pushing the particles together, and then the particles are pushing away from each other because they don't want to be close to each other.
But I mean, the thing is like you get water, and water self-adheres. That's why it forms droplets.
Right.
So like there's